Good day, MP1. Welcome to our post-laboratory discussion for Module 8, which is your last discussion for MT Chem 1 laboratory. For this video, we will be discussing the results and explanations for your Module 8 and Module 9 laboratory manual activities, which is about carboxylic acids and esters and amines and amides. Let's start the discussion first with carboxylic acids and esters. Let's take a look at our objectives. So your objective for the experiment was to determine the physical characteristics of carboxylic acids and esters and to investigate their chemical reactions. For the data and results to be discussed today, we will be discussing the results for the physical characteristics of carboxylic acids and esters, specifically their solubility. And then for the reactions of carboxylic acids, you tested them for their ionization, neutralization, and for esterification. And then under esters, we will be talking about the results for saponification, soap as an emulsifying agent, and of course the hydrolysis of soap. Let's start with the physical characteristics of carboxylic acids and esters. So for their solubility, we were only able to use benzoic acid as our compound. So in water, it is insoluble since benzoic acid is in its solid form. Benzoic acid is insoluble in water and it is soluble in alcohol. So when talking about solubility of carboxylic acids, we have to remember that it contains both the hydrogen bond acceptor, which is the carbonyl group, and the hydrogen bond donor, which is the hydroxyl group. We have to remember that carboxylic acids has both carbonyl and hydroxyl group, and this greatly contributes to the polarity. You still remember one of the notable characteristic of carboxylic acid is that it is the most polar organic compound. That is because of its functional groups, which is carbonyl and hydroxyl group, or if you combine them together, the carboxyl group. As you can see, we have here our hydrogen donor and our hydrogen acceptor. Another thing to remember in the solubility of carboxylic acids is that if there is 1 to 5 carbon in the chain of the carboxylic acid, it is soluble with water. So carboxylic acids with 1 to 5 carbon chain are soluble with water, but higher carbon chain carboxylic acids are less soluble. Okay, but they are still soluble if we are talking about less polar solvent. This is because as your hydrophobic chain, or which is the carbon chain length increases, it becomes less and less soluble in water. But as you can see here, less polar solvents, just like ethers and alcohols, carboxylic acid can be diluted or can be soluble, just like in our result in this one. So we have an alcohol, which is in the experiment, you used an ethyl alcohol. So because of its low polarity, even if benzoic acid 5 or more carbon chain length, it is still soluble in alcohol because it's low polarity. How about the solubility of esters? Low molecular esters are soluble with water. We have to remember that the higher the carbon chain, the lower the solubility. This is also applicable to carboxylic acids. So as the carbon chain length increases or as the carbon number increases, there is a lower solubility for them, which means it's harder for them to be diluted or to be dissolved in water. So the borderline for solubility is 3 to 5 carbon chain. So upon going past this carbon chain length, it's becoming more difficult to dissolve the ester. So we're now done with the solubility of both carboxylic acids and esters. Let's proceed to the different reactions of carboxylic acids, starting with ionization. So in the ionization test, you tested for the conductivity of the following acid, wherein you used a conductivity apparatus, which resulted to HCl producing a bright light and the acetic acid producing a dim light. So what causes this ionization of the acids? We have to remember that carboxylic acids are weak acids that can ionize slightly in water. So in an aqueous solution, only 1% is ionized. So when adding hydrochloric acid and water, it will be producing strong electrolytes because we have to remember that hydrochloric acid is a strong acid. Acetic acid, on the other hand, will produce weak electrolyte because it is weak to moderate acid. So what we have to remember here is that the stronger the acid is, or the higher the acidity of a certain compound is, the brighter the light because it produces strong electrolytes. Next is neutralization of carboxylic acids. So for this part, we used benzoic acid and tried to mix it with water and sodium hydroxide or NaOH. Upon mixing benzoic acid with water, it is insoluble. We have to remember that more than 5 carbon chain lengths will be insoluble in water more. But benzoic acid and NaOH or sodium hydroxide will be soluble. Right? This means that there is a dissolution of benzoic acid or the benzoic acid dissolved. Upon this, there is also a production of a benzoate salt, okay, which is extremely soluble in water. So upon neutralization, when we say neutralization, it is simply the reaction between an acid and a base. So benzoic acid is still considered an acid even if it's just weak. And then our base here is our NaOH. So upon mixing benzoic acid and NaOH, we'll produce sodium benzoate, which is a carboxylate salt, and it is extremely soluble in water. This is also sometimes used as a preservative in some soft drinks, and it can neutralize carboxylic acid. Other reminders is that all carboxylic acids react with strong bases to form water-soluble salt. So these strong bases may be NaOH, just like what you've used in the experiment, or potassium hydroxide. Following neutralization is the esterification reaction, wherein in the results, you need to check for the odor of your compound. So esterification produces a fragrant smell. Sometimes it can be a mild sour smell, or it can also smell like an acetone. When talking about esterification, it's the reaction of carboxylic acid and an alcohol. In here, we need an acid catalyst. So you have your carboxylic acid, react it with an alcohol, and then your acid, which is, I think, is sulfuric acid. And then we'll produce an ester and water. Remember that ester, one of its prominent characteristic is having a fragrant or pleasant smell. Opposite of esterification is hydrolysis. We were not able to do this experiment because of the lack of our reagent. But hydrolysis is when an OR group from the ester is replaced by another group, which is our hydroxide. This is the reverse of esterification. So in this one, you are transforming esters back to its parent carboxylic acid. So you have your ester, adding water, and then catalyze it with a strong acid, will produce a carboxylic acid and an alcohol. As you can see, the OR from the ester is replaced with an OH. So those are the reactions for carboxylic acids. Let's now proceed with esters, focusing on saponification. Saponification is the reaction of a metallic alkali base with fat or oil to form soap. Saponification can happen in different compounds, but for this one, we'll be talking about ester saponification. So this is the process of the formation of soap, wherein you will be adding a metallic alkali or a base, which in our experiment is sodium hydroxide, then a fat or an oil which is the coconut oil, and then you will subject it to heat to catalyze the reaction, and then you will be producing soap. For the results, as an emulsifying agent, okay, upon adding the prepared soap on the mixture of water and oil, which is primarily immiscible, it becomes miscible with each other. So upon adding soap, water and oil were able to mix with each other. As for the hydrolysis of soap, the filtered soap solution turned pink upon adding phenolphthalein, indicating that the soap is basic. Let's talk about first as soap as an emulsifying agent. When we say an emulsifier, it is capable of dispersing or mixing one liquid into another immiscible liquid. So what happens here is that if there are two immiscible liquids, you can add an emulsifier so that they will become miscible with each other. So soap also acts as an emulsifying agent. So how does it do that? Looking at the structure of the soap, we have an hydrophilic group and a hydrophobic group. So when we say hydrophilic, it's water-loving, so it bonds with the water. Hydrophobic group, on the other hand, stays away from the water, but it forms or mixes with our fats, grease, okay, and dirt. And this is what causes our soap to clean. This is what makes soap an emulsifying agent. So in our solution for water and oil, so the hydrophilic group bonded with the water and the hydrophobic group bonded or acted with our oil. Hydrolysis of soap, on the other hand, you use phenolphthalein, okay, as your reagent, wherein you drop phenolphthalein in the soap solution. Phenolphthalein is an organic compound used as a laboratory reagent and a pH indicator, wherein if it's colorless, okay, or there is no change in color, that this indicates that the solution, okay, or the compound is acidic. If it produced a magenta color, which is our result for the soap, it indicates that the solution is a base or is a basic solution. So this tells us that soaps are basic in nature. So those are the data and results for the carboxylic acids and esters. So we've discussed about their solubility, reactions of carboxylic acids, which is ionization, neutralization, and esterification. And then under reactions of esters, we've also discussed about saponification. Take a short break before proceeding to the next part, which is amines and amides. Let's proceed with the discussions of amines and amides. For the objectives, you were asked to describe some of the physical and chemical properties of amines and amides, to identify some tests that can determine the presence of amines, and to differentiate amines and amides in relation to their functional group. For the data and results, so you are asked to observe for their odor. We also tested for their solubility and pH, also noting for their odor. We also did the acetyl chloride test and did the hydrolysis of acetamide, wherein you noted for the odor and for the pH reaction on the litmus paper. Let's start with the physical characteristics, specifically the odor. So for this part, you were asked to look into 3 compounds, but we only had 2 compounds available. I will still be showing the result for dimethylamine. So your sample, which is an ammonia, dimethylamine, and acetamide, their odors, for ammonia, we have a pungent urine-like smell. We've already discussed that ammonia emits a strong, unpleasant odor. Dimethylamine, on the other hand, is a slightly foul-smelling odor and a fish-like odor. Acetamide, on the other hand, has a foul smell and a mouse-like odor, but in small contents or in small quantities, it can be odorless. We're talking about odor. We have to remember that amines are derivatives of ammonia, making them have similar smell with ammonia, but in amines they have slight difference. They are slightly mild in comparison to ammonia. Amides, on the other hand, are generally odorless, but they may still produce a slight unpleasant smell, just like the acetamide. The nitrogen present in both the functional group of amines and amides contribute to their foul smell. We have here an example, which is a urea from ammonia produced in the liver. Urea is processed in the kidney as a waste material and is excreted in our body through urine. So that foul smell of urine, okay, is caused by ammonia. Next is the solubility and pH of both the ammonia and acetamide. So ammonia and water, this is miscible, sorry. And same with acetamide, both of them are miscible in water. And upon adding hydrochloric acid, which is a strong acid, both are still miscible in our solution. So the odor that they produce, for ammonia, pungent smell cannot be observed after adding HCl. Though there is still a slight hint of the foul smell, it is not as strong as the solution before adding the hydrochloric acid. For acetamide, on the other hand, strong pungent odor is notable upon mixing hydrochloric acid. For the pH, before adding HCl, ammonia is a moderate base. Then after adding hydrochloric acid, it becomes a weak base. Acetamide, on the other hand, is already a weak base, and upon adding hydrochloric acid, it becomes a strong acid. Let's discuss first how ammonia reacts with hydrochloric acid. So it's both miscible in water and hydrochloric acid. Mild, unpleasant odor is noticeable but not as strong as a pure ammonia. Okay. So if both in gaseous form, precipitate and a gas fume will form. If we have a gaseous ammonia and a gaseous hydrochloric acid, a precipitate and a gas fume will form, but we only have the aqueous reagent available. For the acetamide, remember that amides are derivatives of carboxylic acids, so they are still considered as weak acids. They produce a sour odor upon adding hydrochloric acid. That is because if you add acetamide with hydrochloric acid, it will produce acetic acid, which is known as vinegar. We're done with talking about this odor, solubility, and pH of amines and amides. Let's talk about the acetyl chloride test. Here is the result for the acetyl chloride test. We have the formation of white precipitate, and we have no reaction, or can simply observe that it's miscible for acetamide. Acetyl chloride is an efficient acetylating agent for alcohols and amines to produce esters and amides. So acetic chloride is an example of an acid chloride, again a derivative of carboxylic acid. And if you mix it with amine, it will produce an amide. Acetyl chloride is an example of an acid chloride, wherein if you mix it with an amine, it will be producing an amide. Going back to our example, so for this one, you were asked to add or to do this acetyl chloride test on dimethylamine, but since we don't have it any available, you were not able to observe their result. So for the ammonia, the formation of white precipitate is quite unnoticeable as the white precipitate are very small in our solution. For this part, we used acetaminophen and added a strong acid and a strong base. So for the strong acid, we use sulfuric acid, and for the strong base, we use sodium hydroxide. For the odor of the acetaminophen and the acid, there is a slightly pungent odor, and the pH reaction on the litmus paper is acidic. For the acetaminophen and sodium hydroxide, the odor is odorless, and then the pH reaction is basic. So acetaminophen is a example of an acetamide, usually known as paracetamol, which is used as an analgesic or a pain reliever, and antipyretic or used to lower down the fever. It is an aromatic compound containing both the hydroxyl functional group and an amide functional group. You can see here we have the hydroxyl and the amide functional group. So hydrolysis of amides can occur with a base or with an acid. So what happens in the hydrolysis of amides is that the carbonyl and the nitrogen bond is broken. As you can see here, the nitrogen bond is broken and is replaced with an hydroxyl. The hydrolysis of amides results to the formation of free acid and a free amine. The result of hydrolysis depends on which catalyst you use. If you use an acid, it will convert amine to amine salt, and then if you use a base, it will convert carboxylic acid to carboxylic acid salt. So it all depends on your catalyst. So we're done discussing the odor, the solubility, and pH of amine and amides. We've discussed the acetyl chloride test, which is a test to transform amines to amides. And we've also discussed the hydrolysis of acetamide. That's it for our post-laboratory discussion for Module 8, wherein we've discussed the reactions and the data of the experiment. Should you have any questions, kindly email me at my AUF email, or you can also message me at Canvas inbox. Thank you and God bless.